Yeah, first of all, thanks for inviting me to give this talk here. So I would like to present a way to construct Lorentzian distance functions on groups of contactomorphisms. And well, so the setting is as follows. So we consider a smooth contact manifold N with a co-oriented contact structure. So psi is the kernel of some contact form alpha. And we want to look at the identity component of its group of contactomorphisms. So meaning the group of diffeomorphisms of N that preserve the contact structure and are isotopic to the identity via contactomorphisms. And Eliashberg and Polterovich on this group defined the notion of positivity. So one can say, given an isotopy of contactomorphisms, that it's positive or non-negative exactly when the contact Hamiltonian defining this isotopy with respect to this contact form alpha is positive or non-negative. So meaning the contact isotopy kind of runs transversely to the contact structure in direction of the co-orientation. And this notion of positivity gives rise to two relations on the group of contactomorphisms. So the first one is, so we can say a contactomorphism phi is smaller than another contactomorphism psi if there exists a positive isotopy from phi to psi. And the same with smaller equal, but we change positive to non-negative isotopy. And moreover, these relations give rise to a natural topology. So sometimes it's called interval topology, just by considering the open intervals of this relation, of the smaller relation. So sets of this form. Well, so it turns out that kind of all these concepts have analoga namely in Lorentzian geometry or in general relativity. And if one considers a Lorentzian manifold, so a smooth manifold with a pseudo-Riemannian metric of index n-1, so means it's, so the metric is not positive definite, but it always has an n-1 dimensional negative definite subspace in each tangent space. One can define similar concepts. So first of all, if we fix a vector field with positive Lorentzian energy, so since the metric is not positive definite, the energy in general can change the sign. So there are tangent vectors of positive energy and some of negative energy, and also non-vanishing tangent vectors of null energy. And especially the ones of positive energy, they define, so the set of the vectors with positive energy has two connected components in the tangent space. So it defines such a kind of double cone in the tangent space. And well, usually one wants to fix in a smooth way one of these connected components, which is called time orientation in Lorentzian geometry. So we fix this vector field, which is kind of the analogon of this, of fixing such a co-orientation in the contact case. And then one can define kind of the analogous notion of these positive isotopies, namely a smooth curve is called, the notion comes from physics, but it's called future pointing time-like or causal if, so first of all, it has positive energy. And second, so the second condition means it's kind of in the, so the tangent vector is always in the connected component of this chosen vector field X. So we again have kind of these positive curves in the Lorentzian manifold. And like in the contactomorphism case, they also give rise to two relations. So we can say 2 points, P and Q, that P is smaller than Q if and only if there's future pointing time-like curve. And the same with smaller equals. So P is smaller equal to Q if there's a future pointing causal curve from P to Q. And in the same way, one can also consider the interval topology of this smaller relation. And it turns out that in kind of most physically reasonable situations, at least, this interval topology coincides with a given manifold topology of the manifold. So in this case, the manifold is called strongly causal. So now to Lorentzian distance functions, which is kind of a more abstract way to look at Lorentzian metrics. So unlike the Riemannian case, there's no natural way to associate a metric to a Lorentzian metric, because it's not positive definite. But instead, there is something called Lorentzian distance function or time separation function. And well, it's a function from, again, n times n, the Lorentzian manifold, to 0, infinity. But yeah, in the Lorentzian case, infinity is really included. So in many situations, it will even take the value infinity between some points. And it's, well, defined in the following way. So we again look at lengths of curves, like in the Riemannian case, but so the square root is only, of course, only defined for causal curves, yeah, because otherwise this metric would be negative. And so we look at the supremum of lengths of causal curves between 2 points. And of course, well, given arbitrary points in a Lorentzian manifold, there does not always exist such a causal curve, so we set it just to 0 in the otherwise. Yeah? And in general, I mean, such a Lorentzian distance function, yeah, it's not always so nice, but at least it has the following properties. So it always induces the smaller relation. So it's positive if and only if P is smaller than Q. Well, because kind of we take the supremum over lengths of curves here in the definition instead of the infimum. One in the Lorentzian case gets this reverse triangle inequality. And the third property, I mean, in general, it's not continuous, but it's lower semi-continuous with respect to the manifold topology. Yeah. And well, I mean, a priori, it can be quite, yeah, maybe useless because in some cases, it can be even just the function which is either infinity or 0. So it does not really carry any information about the Lorentzian metric. But at least in the strongly causal case, so if NG is strongly causal, then like for Riemannian metrics, the Lorentzian metric is uniquely determined by this distance function. And yeah, any bijection of the manifold which preserves the distance function is a smooth isometry automatically. Okay, so now of course, well, the contactomorphism group has similar relations, but it's not a Lorentzian manifold in the usual sense. But one way to generalize the concept of Lorentzian manifold was recently introduced by Kunzinger and Seemann, who kind of defined a Lorentzian analog of metric geometry. So they call it Lorentzian pre-length space. And well, Lorentzian pre-length space is basically, so it's a metric space with two such relations. One of them is assumed to be transitive and the other one reflexive. And the first relation, the smaller relation, should be contained in the second one. So this is sometimes called causal space. And they considered such a kind of Lorentzian distance function on this metric space, which has the following properties. So this object is called the Lorentzian pre-length space. And so the metric space with these relations and this function, if precisely this function here has these three properties of the Lorentzian distance function in the manifold case. So it's positive if and only if x is smaller than y. It satisfies this reverse triangle inequality, and it should be lower semi-continuous with respect to the metric D. So now kind of the goal is to define these structures on group of contactomorphisms. And I mean, the relations were already introduced in the beginning, and it's not too hard to see that they exactly satisfy these conditions. So they are transitive, and the other one is transitive and reflexive. And well, the smaller relation is contained in this smaller equal relation. So the group of contactomorphisms is indeed a causal space. So what is missing is such a metric and a Lorentzian distance function, of course. Well, and a non-discrete reasonable metric was recently defined by Egor Shelukhin as kind of a contact analog of the Hofer-norm on the group of Hamiltonian symplectomorphisms. So so he considered closed contact manifolds, and on such a closed contact manifold, given a contact form alpha, one can define the following norm. So just by looking at the infimum of all contact isotopies which connect the identity with this given contactomorphism phi. And so the infimum is taken of this L infinity length of the contact homotopy. So what Shelukhin showed is that this is indeed a norm. So first of all, it satisfies that it's zero if and only if phi is the identity. So secondly, it satisfies this triangle inequality with respect to composition, and it kind of behaves nicely with respect to taking the inverse and this conjugation. I mean, in general, I should say maybe, so it's not bi-invariant, because there's a result that that any bi-invariant metric on the group of contactomorphisms has to be discrete, and in particular, this norm depends on the choice of a contact form. So the only thing that one has is that if we conjugate kind of the contactomorphism, then this is the norm of the pullback of the contact form. And so we wanted a metric. So any norm of this kind gives rise to a metric in this way. So the metric between two contactomorphisms is just the norm of psi minus 1 composed with phi. Okay, so now we have our metric, and what is missing is the Lorentzian distance function. And kind of in a similar way, like this Shelukhin metric, or Shelukhin-Hofer metric, one can define a Lorentzian distance function in this way. So by looking at the supremum over all non-negative isotopies which connect two given contactomorphisms, and instead of the maximum or the L infinity length, we look at kind of the minimum of the contact homotopy. Of course, only if, like in the Lorentzian manifold case, only if there is a non-negative isotopy connecting these two contactomorphisms. And again, we set it to 0 in the other case, so if there's no non-negative isotopy. Okay, so now the first result I would like to present is, this is really a Lorentzian pre-length space. So in particular, this distance function tau alpha satisfies these three assumptions. So it's positive if and only if the contactomorphism phi is smaller than psi. It satisfies this reverse triangle inequality. And it's not only lower semi-continuous, but one can show that it's always continuous with respect to the Hofer-Shelukhin distance. And additionally, so if one assumes that the smaller equal relation is a partial order on the group of contactomorphisms, which I think it's kind of equivalent to say that there are no positive loops of contactomorphisms. So this is, for example, the case for many unit cotangent bundles due to a result of Chernoff and Nemirovsky. So in this case, if this is a partial order, then one can show that this Lorentzian distance function is indeed finite. So it never takes the value infinity between two contactomorphisms. Okay, so I mean, I should say the proof is kind of maybe elementary, so it does not really involve any higher techniques of contact topology or symplectic topology, but is more or less based on modifying given isotopies in a clever way. But the same kind of ideas can show the following results. So first of all, so this is basically contained in the proof of this theorem. So one can show that the interval topology on the group of contactomorphisms, so meaning the topology induced by this smaller relation, this is always coarser than the topology induced by the Hofer-Shelukhin distance. So of course they do not always coincide. So because, for example, in the case when this smaller equal relation is not a partial order, so there exists positive loops of contactomorphisms. In this case, the interval topology will, I think, in general, not be Hausdorff. So it's really strictly causal than this topology induced by this metric. Yeah, and the second result one can show is indeed, again, so if this is a partial order, so if there's no positive loop of contactomorphisms, and one considers the rate flow of the same contact form that defines the norm, yeah, and let's say positive t, then indeed the Hofer-Shelukhin norm of this rate flow at time t is precisely t, yeah, and coincides with the Lorentzian distance function. So kind of that means the rate flow of this given contact form alpha is, maybe one could say, a geodesic for the Hofer-Shelukhin norm, and also a geodesic for this Lorentzian distance function. Okay, so that was all the results I wanted to present. So maybe some close with some open questions I find interesting. So first of all, yeah, so kind of all the causality conditions for Lorentzian pre-length spaces that are considered so far in the group of contactomorphisms are kind of saying if this if this relation, the smaller equivalation, is partial order or not. Yeah, so if there exists a positive loop of contactomorphisms or not. But sorry. But maybe, yeah, it might be interesting if there are indeed contact manifolds which are strongly causal. So in the sense that the interval topology really coincides with the topology induced by this Hofer-Shelukhin distance. So I mean, I tried to show it for some examples like unit cotangent bundles or jet spaces, but yeah, it did not really work. And I mean, I believe if it is true, it kind of involves more advanced techniques like spectral invariance or things like this. So it might be quite hard to show. Yeah, and the second question is, of course, so this Lorentzian distance function is not bi-invariant, so it depends on choice of a contact form. Yeah, so the question is, are there more natural Lorentzian distance functions one can define on the group of contactomorphisms? So meaning, are there kind of meaningful bi-invariant Lorentzian distance functions other than kind of the trivial one? So of course one can always look at this kind of trivial Lorentzian distance function, which is just saying, so yeah, it's infinity if phi is smaller than psi and just zero otherwise. Yeah, but kind of the question is there a Lorentzian analog of the statement that every bi-invariant metric on the group of contactomorphisms has to be discrete? Yeah, maybe I should also say, I think it does not really make sense to consider discrete Lorentzian distance functions, because I guess due to this reverse triangle inequality, kind of all of them would look like this. Yeah, so they would be just infinity if phi is smaller than psi and zero otherwise. So okay, so I think that was all I wanted to say. So yeah, thanks for your attention. And,
thank you. Okay. Yeah. Any question?
So maybe can you say a word about which methods you are using in order to prove that Lorentzian distance is less or equal than this Hofer-Shelukhin distance?
So you mean, so this is another result, which I kind of did not present here, right? But I think, I mean, one could show in the case of, so you mean that the Hofer-Shelukhin, that this tau alpha is less or equal than the Hofer-Shelukhin?
Yes. So you did not mention it here.
No. It was just in the kind of paper where I.
Okay, but maybe okay. So very good. So then mention it and
comment. So yeah, I think in the case of yeah, it was in the case of certain unit cotangent bundles or jet spaces where one can use spectral invariance, and there are kind of estimates of so in terms of spectral invariance exactly of so this integral of the minimum of the contact Hamiltonian is less or equal to some spectral invariant is bigger or equal to this maximum of the contact Hamiltonian. And kind of these estimates one can use to say, and on one side I take the infimum of this so the Hofer-Shelukhin distance is basically taking the infimum of all such paths of the L infinity length, and on the other side I have I take the supremum over all minima of the contact Hamiltonians, and then like the supremum and infimum is always then bounded by these spectral invariants. So one then gets that kind of in these cases that this Lorentzian distance function is always smaller or equal to at least, let's say, some constant times the Hofer-Shelukhin metric.
Okay. Thank you very much.
Other questions?
Yes, so what exactly can one do with Lorentzian pre-length spaces? So in the kind of Riemannian counterpart, right, you can define below or something like that for geodesic metric spaces, something like that.
Yeah, exactly. So I mean, maybe with what's the definition? So I mean, maybe with Lorentzian pre-length spaces like this, not that much. But I mean, of course, one can define the notion of geodesic, kind of similar to metrics or to length spaces. But so what I didn't define is the notion of Lorentzian length space, which of course also exists, and this involves more, kind of more properties of geodesics. So then one needs so Lorentzian pre-length space being a Lorentzian length space means that kind of there are properties like local existence of geodesics between two points in this Lorentzian pre-length space and things like this. And if this is satisfied, which I don't know, I mean, it might be hard to show, but it might be true on the group of contactomorphisms. So if this is really a Lorentzian pre-length space, then one can also define kind of Lorentzian analog of these Alexandrov spaces or things like this, and talk about curvature and triangle comparison, things like this, and then say maybe the curvature of such a Lorentzian length space is bounded from below, or it's constant, or things like this. So, but as I said, I mean, I don't know if first of all one would have to show properties of these of this Lorentzian distance functions for contactomorphisms before doing this. So.
And I guess you would have to look at explicit triangles of geodesics, even if you were in the Lorentzian length.
Exactly. But so the first question is, what are actually the geodesics in the group of contactomorphisms? So, I mean, we know one of them, which is like the Rebflow somehow of this contact form alpha. But so, I mean, maybe I would conjecture that it's like that they are also. I think it's like this for the Hofer-norm Hamiltonians, right? That they are kind of quasi autonomous Hamiltonians or something like this, that they have a fixed minimum or maximum, and maybe it's like also like this for this Lorentzian distance function, so that they are kind of so they have a fixed positive minimum or a fixed positive minimum and maximum like this. But I'm not sure.
Thank you.
Okay, any other question?
Did you generalize this to the spaces of Legendrian submanifolds?
Yes, indeed. So one can define the same. So I mean, there's also this notion of positivity for Legendrians, right? So saying kind of isotopy of Legendrians is moving positively transverse to the contact structure. And also in this case, one can. So first of all, there's a kind of analogous metric defined by Rosen and Zhang, which is kind of taking uses also the Hofer-Shelukhin norm, so it takes the infimum over all contactomorphisms that map a certain Legendrian to a certain other Legendrian. And using this distance, one can actually show the same results. So one can also define this Lorentzian distance function as kind of the supremum over all paths of contactomorphisms, positive paths, which map a given Legendrian to another Legendrian, and then taking the minimum over this Legendrian, kind of instead of n. And basically one can show the same results. So this is also a Lorentzian pre-length space, and which is also satisfies these conditions.
Thank you.
Okay, so I guess we can thank again Jakob.